Hello and welcome to our notes on section 1211. Today we're going to be talking about binomial probability. We're going to start by discussing something called a probability distribution. And a probability distribution is a distribution in which the probability of every possible outcome of an experiment is listed. And the sum of all these probabilities will always equal 100%. So let's go ahead and find the probability distribution for each experiment and show that the sum is 100%. So if we're flipping a coin, you can get either a heads or you can get a tails. So what we need to do is find all the probabilities that can happen. So we can get the probability of heads, which is 1/2. And then our other option is we can find the probability of getting a tails, and this is also 1/2. Okay, and you'll notice that our total probability is 1/2 plus 1/2, which equals 1, or 100%. Next, a normal six-sided die is rolled. So when we're talking about a six-sided die, we have the options of a 1, a 2, a 3, a 4, a 5, or a 6. So a probability distribution is just going to show that each of those probabilities. So the probability of getting a 1 is 1/6. The probability of getting 2 is 1/6. The probability of getting a 3 is 1/6. The probability of getting a 4 is 1/6. The probability of getting a 5 is 1/6, and the probability of getting a 6 is 1/6. Alright, so there's our probability distribution, and if you notice it, when we add all of these up, they do add up to be 100%. Okay, because we have 6 1/6 present, and that's 100%. Now the binomial probability can be used when there are n independent trials, when each trial has two outcomes, either success or failure, and the probability of success or failure remains the same for each trial. So a note on that is that everything has to be done with replacement. Now we're going to try example 1 without our probability formula first. It says a normal six-sided dice is thrown 5 times. What is the probability of getting the number 1 3 times? Okay, well, the probability of getting the first one would be a 1 is 1 out of 6. The probability that the second one is a 1 is 1 out of 6. Probability that the third one is a 1 is 1 out of 6. Now we need 2 that are not a number 1, and so the probability of not getting that would be 5 out of 6, and then 5 out of 6. So this is kind of using our fundamental counting principle here and our AND formula. So you can see we have 3 number 1s and 2 not number 1s. But the problem is the order that this happens does not matter. What else do we know about probability that is used when order does not matter? Well, a combination. So these events right here can happen in any order, meaning we're going to multiply by the number of ways they can happen, which is going to be, well, we're throwing the die 5 times, and we want exactly 3 1s. So this is the number of ways that can happen, and so we're going to multiply right there. And so what we've just done is actually use the binomial probability formula. So let's talk about the binomial probability formula here for a bit. It says P of x equals NCX times P to the x power times Q to the n minus x power. Okay, so let's talk about what each one of these means. So P of x is the probability of getting exactly x successes. Alright, x right here is the exact number of successes. N is the total number of trials. P is the probability of success on one trial. And then Q is the probability of failure on one trial. Okay, so let's go ahead and try and use our binomial probability formula over here and see if we come up with the same thing that we just reasoned. So here we need to find n, which is the number of trials, and it looks like we're throwing a dice 5 times, so n equals 5. X is going to be how many successes we want. Well, we want getting the number 1 3 times, so we have 3 successes. P is the probability of success, so the chance of getting a 1 is 1 out of 6. And then Q is the probability of failure, and so that's going to be 5 out of 6. So we always need to identify these 4 things whenever we're doing the binomial probability formula. Applying this, we want the probability of getting exactly 3 ones in 5 trials. So it's going to start off 5C3 because we want 3 out of the 5. And then it's going to be times the probability of success, which is 1/6, to the power of how many times we want that success. So to the power of x, which is 3, times the probability of failure, which is 5/6, to the power of the number of times we want a failure. So in this case, we actually do n minus x, and I'm just going to put a note here, n minus x in this case would equal, well, 5 trials minus our 3 successes gives us 2 failures. Okay, so we want our 2 failures right there. Now, if we analyze this, 1/6 to the 3rd power is exactly what we have right here. And then 5/6 to the 2nd power is what we have right here. So this indeed is the same formula. And you would type this straight into your calculator just like this, and we get about 3.2%. Alright, so that is how we use the binomial probability formula. Now in example 2, it says a basket contains 3 marbles, 1 red, 1 blue, and 1 yellow, and 3 marbles are to be selected with replacement. So very important that to be able to use binomial probability, it has to be with replacement. So we want to know what is the probability of selecting 0 marbles, 1 marble, 2 marble, or 3 blue marbles, and then also at least 2 blue marbles. So looking at A, B, C, and D, we're basically coming up with a probability distribution for this. Now, we could have solved this using what we already know about probability. So if we want the probability of getting exactly 0 blue marbles, yeah, we'll just change it to red marbles. So 0 red marbles here, what I've done is I've made a tree diagram of what's happening here, and I've made our sample space right here as well. So looking at this, what's the chance of getting exactly 0 red marbles? Well, we want all the ones that don't have red in it. So there's one, there's one, there's one, there's one, there's one, there's one, and there and there. And so if we add this up, looks like I have 2, 4, 6, 8. So that's going to be 8 out of 27. Okay, next let's talk about getting exactly 1 red. So we need all the ones where there's exactly 1 red. So it looks like here, 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 and here. Okay, those 3. Here's another one. Here's another one. Here and here. And I think that's it. So 2, 4, 5, 6, 7, 8, 9, 10, 11. Oh, there's one more right here. So this one is going to give me 12 out of 27. All right, and getting exactly 2 reds. Okay, so we have one here, and here, and here, and here, and here, and here. So we have 6 out of 27. And the chance of getting 3, exactly 3, yeah, looks like just that one right there. So that's going to be 1 out of 27. Now, if we find the sum of all of these, 8 plus 12 is 20, plus 6 plus 1 is 27, we do get 27 out of 27, which is our 100%. So we can answer all of these questions by making a sample space and then counting just like so to get each of our answers. But now let's take a look at how we can use the binomial probability formula to help us out. For each of these problems, n is going to be the number of trials, and it says 3 marbles are to be selected, so n equals 3. The probability of getting a blue marble is always going to be 1/3 because there's 1 out of 3. And then the probability of failure is always going to be 2/3. So these 3 things are not going to change for our probability problems at all. The only thing that changes is our x. And so in letter A it says exactly 0 blue marbles. So here x is going to equal 0. So the probability of getting exactly 0 marbles in 3 tries is going to be 3c0 times 1/3 to how many successes we want, which is 0, times the probability of failure, 2/3, and how many times we want that failure, which would be 3 times. And if we use our calculator here, we do get 8/27. Okay, and if we compare that to what we got here, you'll notice we had gotten 8/27 as well. All right, if we want to get exactly 1 blue marble, now x is going to equal 1. So the probability of getting exactly 1 blue marble in 3 tries is 3c1 times your probability of success, which is 1/3, and how many successes we want is 1, times the probability of failure, which is 2/3, times how many failures are going to be, and we get 2. And one thing to note here, that the 1 plus the 2 is going to equal the 3. Okay, so these two up here always have to equal the 3 right there. And when we try this in our calculator, we get 4/9, which is the same thing as our 12/27 that we had gotten looking at the sample space. All right, let's try it with exactly 2 blue marbles. So here x is going to equal 2. So the probability of getting exactly 2 in 3 trials is 3c2 times the probability of a success, how many successes we want, times the probability of failure, times how many failures we want. Okay, and looking at this, we're going to get 2/9. Okay, which again is our 6/27 that we had gotten before. And finally, exactly 3 blue marbles. So here x is going to equal 3. So the probability of getting 3 blue marbles in 3 tries. So 3c3 times the probability of success to how many successes we want, all 3 of them, times the probability of failure and how many failures we want. We don't want any. And when we calculate this, we get 1/27. So you can see we ended up getting the same answers as we had by looking at the sample space, but this way is much quicker to find it. And when we add all these up, we do of course get 100%. Now, the next question is a little bit different. It says, what's the probability of getting at least 2 blue marbles? And what this means is 2 or more. And in this case, 2 or more means getting 2 or getting 3. So when we look at this, we think, well, x has to equal 2 or x has to equal 3 for our exact number of successes. And when we have an OR formula, what do? We add the probabilities. So anytime you get at least, you're going to have to take 2 or more, and so however many that is, and you add up all the probabilities. So here we would do the probability of 2 plus the probability of 3. Okay, so we had already found the probability of 2 was 2/9, and the probability of 3 was 1/27. And when we add this together, right, because that's times 3/3, so 6 plus 1 equals 7/27. So if you have a probability distribution, finding the at least is not too bad. You just take that one and you add all the ones above it. Now we can also use the TI-83 to get the probabilities for a binomial probability distribution. And there's just a very simple step. You're going to go ahead and press second vars, which I think is actually dister, standing for distribution. And then you select the option Binom PDF. So a binomial probability distribution. And that's what we're looking here. And then you complete the entry to obtain Binom PDF NPX with the appropriate values substituted in. So it's the same NPX that we were using before. Okay, so example 1 says on a 10-question multiple choice test with 4 options per question, the probability of getting 5 and only 5 answers correct if the answers are guessed. So here in this case, n is going to equal 10 because it's a 10-question multiple choice test. The probability of success is going to be 1/4 because there are 4 options per question. And x here is going to be 5 because we want to find the probability of getting exactly 5 out of the 10 correct. So in your calculator, you're going to go Binom PDF and then type in 10.25 and 5. You could have left 1/4 there as well. When we do this, we would get an answer of 5.8%. And we can also use a tool called Wolframalpha. Okay, so it's just a website, wolframalpha.com, and we can just type in Binom PDF, and then in parentheses we're going to list n, p, and x. So n was 10, p was 1/4. Now here you do have to use a decimal, so you have to use 0.25. And then x was 5, so we're going to hit 5, and then go. So looking at the input information, it said our input was 5, and that is our x, our number of successes. Our success probability is 0.25, and the number of trials is 10. So that is correct. Now looking at the probabilities, what we're looking for is when x equals 5. Okay, and there is our 5.8% that we had gotten using our other calculator as well. Now down here, looking at the plot, it's showing all the possibilities for 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And you can see the probability of guessing all 10 correctly just drops off dramatically right there. Now, in this case, if we were looking for at least 5, well, what we would do is take 5 or more. Well, the probability for 5 was 5.8%. And then this or more is going to be actually greater than 5, which you can see is right here. And so it actually adds up. Okay, here was 5, and it'll add up all of these probabilities for you, and that was 1.9%, or about 2.0%. And so if we wanted at least 5, we would simply have to add these two guys together. So we would get 7.8%. Okay, so just another way of solving an at least problem without doing the binomial probability formula a whole bunch of times using Wolframalpha. All right, I want you to give problems 1 through 4 a try on your own. Go ahead and pause the video and then come on back to check your work just to make sure that you know how to do this. All right, welcome back. For number 1, should have gotten 26.1% here. And our n was 50, our p was 0.05, and then our q is always going to add up to be 100%, so that was 95, and we're looking for exactly 2. So just using our binomial probability distribution formula, we would get 26.1. For number 2, the probability of getting at least 2 heads would be 2, 3, or 4. So n here was 4, p is 1/2, so q is 1/2. And we would add up these 3 probabilities right here. And so you can see using the formula 3 times, and we add all this up and we get 68.75%. Now using your calculator or Wolframalpha, all you have to do is identify n, p, and x actually. So n here is 5, p is 0.8, and x is 3. We don't even need q to do this. So just binom PDF, npx, you should get 20.48%. And for number 4, it was at least 2, meaning x had to be 2 or 3 or 4 or 5. And here n was 5, p was 0.4, and again, you don't really need q to solve these. And so all we had to do was do binom PDF with 2, binom PDF with 3, binom PDF with 4, binom PDF with 5, and then add them all together. Should get 66.304%. All right, so that is probability distributions and using the binomial probability formula.